discussing descriptive statistics, mostly how to present the data in graphical and chart format. Now, this chapter 3 is a continuation of descriptive statistics, but this time we're talking about numerical measures. Okay? So instead of presenting the data in graphical or visually pleasing form, many times we need to present the data, basically summary statistics, summary characteristics, okay, using some numbers and some other format. So this will be the second half of the descriptive statistics. Typically, we present the data characteristics in three different types of information. First one is central tendency, and the second one is variation, and the lastly, shape of distribution. So many times you would see something like this. Okay. Does anybody have any idea what this is about? Have you ever seen this before? Okay. This is a very succinct way to present the data. What that means is there is one unknown variable, or what we call random variable, okay? And this is distributed, this tilde. In statistics, we just read it like distributed, okay? So x is distributed normally with the mean value of 0 and the standard deviation of 1. So this is specifically what we call standard normal distribution. Among many different types of normal distribution, there is one particular shape and size, or more exactly shape of distribution. It's called the standard normal. So here we presented all three information. First of all, central tendency, by specifying the central location or mean value, and this one represents spread or dispersion, how widely the data points are scattered. So if we have any normal distribution, we have specified where it is centered, how widely the data points are scattered, okay? And finally, the shape of the distribution. We're saying this particular random variable is distributed normally. It has normal shape, okay? Well, of course, we haven't discussed normal distribution yet. It's the topic of chapter 6, so don't worry about it if you don't understand, okay? But that's where we are headed, okay? So central tendency is the extent to which the data value groups around a typical or central value. The variation is the amount of dispersion or scattering of values, how widely the data points are scattered. And finally, the shape. Okay, this what we call normal distribution, nice looking distribution, but in reality, when you have any random variable, it doesn't have to have this nice, normal distribution. You can have some asymmetric distribution, or you can even have some weird shape distribution. There can be all kinds of cases, okay? All right, so in this chapter we're going to talk about these concepts. Let's first talk about the central tendency. And we're going to talk about a few different measures or measurements of central tendency. The first one, and most frequently used one, is called the mean. And since you are very familiar with this, you've been using this for many years in your life already, okay? So I'm going to be very brief, okay? In other words, mean is the same thing as average, or arithmetic average, arithmetic mean, okay? And as you know, how do we calculate the mean? Just add them up when you have different, how many observations. N typically refers to the number of observations, observations in a data set. Okay? So you just add them up and divide by the number of observations. If you have 10 numbers, add them up and divide by 10, and that's how you calculate the mean. Okay? Here we put a bar on top of x. I think I mentioned this in the first class. This is the expression, typical expression for sample mean when we have when we calculated the mean based on the sample data. Okay? And population parameter is called the mu, Greek letter mu. Okay? So eventually we're going to be making inference on population parameter using sample statistic. Okay? That's towards the end of the semester. All right, so that's it. Any question about mean? I guess not. Okay. There are a few things that we need to know about central tendency, especially the mean. Okay. Of course, the mean is the most common measure of central tendency, and that's how we calculate the mean. Okay. One important characteristic of the mean is it is affected by extreme values or outliers. Okay? And we have one example or a couple of example distribution here. Suppose we have 5 numbers. We have 11, 12, 13, 14, 15. Okay? And what is the mean of those numbers? Well, you don't even need to calculate it, right? Because they are all evenly distributed with one distance. Okay? The center, 13, will be the mean value of those 5 numbers. Okay? But we had, suppose, 11, 12, 13, 14, but one last number was pretty large, like 20. Okay? Then, immediately the mean changes. Okay? Mean becomes 14 instead of 13. Okay? So when we have some extreme values, the values that are quite different from the rest of the values, then mean changes. Mean is sensitive to extreme values or outliers. Is that a problem? Well, in certain cases it is. Okay? We'll talk about it in the coming slides. So many times, instead of mean, we talk about median. Okay? Median is another measurement for central tendency. And the definition is, well, it's the number in the middle, which means that particular number has 50% of the observations below that number, 50% above that number. Okay, it's right in the middle. That's the idea or concept of median. Okay, so using the same example, when we have 5 numbers, if you have 11, 12, 13, 14, 15, well, median will be exactly 13 because it has 2 numbers below that number and 2 numbers above that number, right? So in that case, mean will be equal to median in that particular case. Okay. What about the second distribution, 11, 12, 13, 14, and 20? Okay. Then median will be 13. Because regardless of the last number 20, it still has 2 numbers below 13 and 2 numbers above 13, right? So the concept of middle number, median, is exactly 13. Okay. So here we can see the fact that median is not affected or not sensitive to extreme values. Extreme values really do not affect median. Okay? So, depending on what you are measuring, is it me or? I'm not feeling really perfect today, so maybe it's me, and I hope. I don't know what's going on here. let's continue and see what happens. Okay? All right. So let's say you are interested in average or mean height. Somebody's playing around with this. Let's say we're interested in finding out the mean height of students in this room, about 50 students in this room, right? Should we use mean or median? Median? Mean? Which one? Make up your mind. Why? Let me give you another case. Let's say you're interested in average income of the population in this community, let's say, within Haengdangdong area, or let's say even among the Hanyang University students. Okay? What will be the difference between these two cases? And which one should we use? Should we use mean here or median for each case? What should we ask? What's the question we should ask for this answer? What's the difference between mean and median? What are we talking about here? One is sensitive to extreme values, the other is not sensitive, right? So that should be the criterion, right? So, average height of people are relatively similar. They're distributed within narrow range, okay? Some people, I don't know, maybe 1 meter 40 centimeters, right? And some people are tall, maybe 2 meters, right? But it's not like some people are 20 meters tall and some people are just 20 centimeters tall, right? So when we're talking about heights, there aren't really a lot of extreme values, okay? But income, we can easily imagine the situation, right? Some people have income which is 10 times larger than even 100 times or 1,000 times larger than income of other people, right? So typically when we talk about the average income or average home values, okay, we tend to use median instead of mean, okay? If you're talking about the average height or weight, so on, right? More popular uses will be the mean for these cases. Okay? Does it make it clear? Right? When to use mean, when to use median? Okay? All right. So the concept of median is simply the middle number, but it requires a little bit of thinking. If it was an odd number distribution, something like this, we had 5 numbers, right? Then it's easy, right? It's always middle right here, right? So third number is a median here, and third number is the median because it has 2 above, 2 below, right? But what if we have even numbered observations in our data? So for that purpose, we use this position, right? We have to come up with the median position. Median position is n plus 1 divided by 2. N is, of course, number of observations, okay? So if you have 5 observations, 5 plus 1 divided by 2, which is 3, right? That's how we found the position of the median number in the previous slide, right? So what if we had 6 numbers? I mean, number of observation was 6, right? There would be 6 plus 1 divided by 2, which would be 3.5, right? But there is no such number on 3.5 or 3.5 number, right? So in that case, it would be the median is the average of the two middle numbers, right? So if the position number came out to be 3.5, right? That means the median should be the average of third number and the next number, third and fourth number, right? Okay. So that's how we should come up with the median number, how to find the median. Is it clear? Okay. And finally, among the central tendency measurements, we also have what's called the mode. Okay? Mode is just most frequently observed value, or value that occurs most often. Okay? So when we have many numbers distributed, okay, it is possible that we could have multiple observations of the same number, like this. Okay? So here we have 1, 1, 1, 3, 2 5s, 1, 7, 3 9s, and so on. Right? Then, for this data, the mode will be 9, because 9 is the number that is observed most frequently, okay, in the data. Okay? And obviously, in the case like this, we cannot find any mode, right? Because they are evenly distributed. All numbers are equally frequent. Okay? So there may be no mode, but it's quite possible that there may be several modes, more than one mode. Okay? So here, in this case, suppose we didn't have these 3 observations for 9. Okay? We had 2 5s and 2 12s, but no 9s. Okay? Then in that case, we will have 2 modes. Modes would be 5 and 12. We will have 2 modes. Okay? We have specifically, it's called the bimodal distribution. Okay? Which means distribution has 2 modes. Okay? But it is also possible that we can have multi-modal distribution. Some distribution can have multiple modes. Okay? If you have, say, 2 5s, 2 9s, 2 12s, okay? Then we have 5, 9, and 12 as our modes. Okay? Pretty simple. Okay? Another interesting thing about modes is not only numerical data, but for categorical or nominal data, we can talk about modes as well. Okay? Let's say you are interested in finding people's favorite color. Okay? So if you ask, well, among the 7 colors in rainbow, okay, what's your favorite color to the students in this class? Okay? Then response may be, well, red. First person says red. Second person says yellow, blue, red, blue, green, blue, and so on. Okay? Suppose you asked, what, 7 people. Okay? Then we have 3 people responded blue. 2 people responded red, right? So in this data, well, of course this is a nominal data, categorical data, right? But we still have mood. Mood is blue. Okay? That's an interesting thing about mood. Okay? All right. So here's one very simple example, hypothetical example. Let's say we have 5 houses, and the prices of these houses are distributed that way. Then the mean value of houses is 60,000, I guess, dollars. Okay? But the median is 30,000. So we see quite a significant difference between mean and median. There's a lot of discrepancy between mean and median, right? Why does it happen? Even though median was 30,000, mean is 60,000. Why does it happen? Yeah, there is one extreme value, right? The 4 houses are distributed within pretty narrow range between 10,000 and 50,000, but there is one house which is extremely valuable, or is it $2 million? Okay, $2 million. Okay, so that just brings the mean value up so much. Okay, mean is sensitive to extreme value. Okay, all right. And the mode in this case is 100,000, because there are 2 houses with the $100,000 value. So here's a kind of summary. Among those 3 measures of central tendency, okay? Mean is generally used, most frequently used. But you have to be careful when there is any extreme values or outliers. Okay? Median is often used when there are extreme values. Right? We talked about this already. Okay? And many times it makes sense to report mean and median together. Okay? In reality, we tend to report both of them together. Okay? In many cases. All right, one additional item about the central location or central tendency is called the geometric mean. And this is not very frequently used. Okay? Geometric mean, probably in engineering they use this more often than in business or economics. Okay? But the idea of geometric mean is when you have n numbers, you multiply all n numbers and take nth root. If you do, okay, I guess here I need to introduce one, I guess, common sense item just to help you in case you go to study abroad. Okay? When I first went to the United States to go to graduate school, I didn't know how to read something like this, right? In English, right? How do I say this? Let's say. Okay. This is, you can say y raised to the power of x. If you want to say exactly y raised to the power of x, right? Or y to x, okay, something like that, right? Is that right? Y to x. Yeah, y raised to x, something like that, right? If you have something like that, x1 to the power of 1 over n, right? You can say this is nth root of x, because it's the same thing as, right? Okay, nth root of x. So geometric mean is nth root of the product. Okay, when you multiply all those numbers, it's also called the product. Okay? Product of all the observations. Okay? That's what we call geometric mean. Okay? So slightly different. Instead of adding up and divide by n, right? Now multiply everything and take the nth root. Right? That's the geometric mean. Okay? Of particular use for business and economics is mean rate of return. Mean rate of return. Okay? So let's say you made an investment for multiple years. Okay? And every year the rate of return can be different. Okay, so first year you made 10% return, second year you made 5% return, and so on. Okay. Then after 10 years, you want to find out what was the average rate of return on this investment. Okay, and this is how we calculate that. So in my example, R1 would be 10% or 0.1, so 1 plus 0.1. Okay, multiplied by 1 plus, if second year's return was 5%, it would be 0.05, right? So 1 plus 0.05, and so on, okay? And then, after multiplying all those, you take nth root, okay? So if you have 10 years, this will be 1 over 10 to the power of 1 over 10, okay? Minus 1, okay? That would be the mean rate of return for your investment. Okay? So, you know, you can think about many different situations. Instead of rate of return, you can talk about growth rate. Okay? If your salary, think about it, let's say. So you start working, and the first year, after the first year, your salary went up by 3%. The second year, well, it was not good, company was not doing well, okay? So they didn't give you any real raise, so 0%. And the third year, you get 5% raise, and so on, right? Then you can calculate the average growth rate of your salary, okay? Or, you know, if you're running a business, you might be interested in finding out what's the average growth rate of your sales, for example. Okay? So you can use these numbers to find out the mean rate of growth or mean rate of return. Okay? Okay? So here, very simple hypothetical example. Okay? So let's say you made a $100,000 investment. In the first year, it was bad. You actually lost money. Okay? So something happened to the economy, or there was a financial crisis. Okay? So in the second year, it went down to 50,000. Okay? So you lost money. Your investment lost the value by 50%. Okay? But let's say the next year was pretty good. You recovered everything, right? So from 50,000 to 100,000, that's a 100% increase. Okay? Rate of growth was 100%. Okay? So in this case, if you calculate arithmetic mean, the typical, average, okay, then you would say negative 0.5 because you lost 50% of the value in the first year. In the second year, you made it up. It was 100% increase. So you use plus 1 and divide by 2. Then you get 25% return or 25% growth, which is not true, right? Because you started with 100,000, ended with 100,000, so growth rate was actually 0 over those 2 years, right? So this is a misleading result if you use arithmetic mean, okay? But if you use geometric mean of return, right, then if you use this formula, 1 plus negative 0.5, 1 plus 1, and take the square root or second root, yes, square root, okay, minus 1, okay, and you would come up with the 0%, which is exactly true, right? You started with 100,000, ended up with 100,000, okay? So growth rate was 0. Average growth rate was 0 over those 2 years, okay? Any question about the geometric mean? Okay? All right, as I said, I'm going a little bit fast here because you're pretty familiar with the mean and so on. Okay? So this is just a summary. Arithmetic mean, median, mode, geometric mean. Guess we don't need that. All right, second type of measurements when we try to describe a data is variation. Again, the concept of variation is how widely the data points are scattered or spread. Okay? So it's a measure of spread or variability in the data. Okay? Well, let me tell you a story. Why do we need this spread? Okay? Maybe I mentioned it, but I am an advisory board director for a small company in North Carolina. They are a plastic manufacturer. Okay? And they have supplied to Hyundai and Kia automobiles. Okay? Hyundai has a plant in Alabama, Kia has a plant in Georgia. Okay? And from North Carolina, you go across South Carolina, that's Georgia. And next to Georgia, that's Alabama. Okay? So we are the second tier supplier. Okay? So when Hyundai and Kia produce their automobiles, okay, they first design the car, a new model, okay, and they call up their first tier suppliers. First tier suppliers, okay, and they give order to first tier suppliers. I guess the one you know probably would be Mobis. Mobis is probably the best known first tier supplier to Hyundai and Kia. Okay? But there are many other first tier suppliers, Haniliwa, of America. Okay, they use it. Haniliwa is a company in South Korea, but they have branch in, I guess all the first tier suppliers have their locations in the United States because they have to supply to Alabama and Georgia plant. Okay? Another one is SL. Have you ever heard of SL? The original company name was Samlip, okay? But not Krimpang. Okay? This is a company which makes automobile parts. Okay? So a few years ago they changed their name to SL. Okay? So we supply to these first tier suppliers. Okay? So when these companies get the order from Hyundai and Kia, some of them they produce themselves, okay? But a lot of items they give order to second tier suppliers. Okay? So once I visited SL location in Alabama with some of my company people. Okay? So we went into the meeting room, and there's a whiteboard in the meeting room. Okay? And in the whiteboard, I saw something like, let's see. Something like that. Okay? And here, KJ. Okay? So, since I teach statistics, I was quite interested as I asked 구부장님, Mr. Ku, what is this? Do you guys talk about, or do you guys teach statistics here? Okay? And he explained it to me, and he said, well, one of the major items that SL produce are headlamps. Headlamps, okay? You know what, headlights. These days, the headlamps are pretty big. If you look at automobiles, especially SUVs, right? The size of headlamp is pretty big, right? But very long item. Okay? So it's a very valuable item. Okay? And inside the headlamp, there is actually light bulb. Okay? So they're trying to decide which light bulb to use, a Korean-made light bulb versus Japanese-made light bulb. Okay? And this is the life expectancy of two different light bulbs. Okay? And apparently, I don't know, maybe 2,000 hours, and this may be 2,100 hours. Okay? So according to statistics, Japanese light bulbs last slightly longer than the Korean light bulb. Okay? So in terms of central location of the distribution, you can say Japanese bulbs are better than Korean bulbs. Okay? But another interesting thing is there's a difference in the spread. Okay? So Korean light bulbs, the spread is narrower than the Japanese light bulb. In other words, Korean light bulbs are more consistent than Japanese light bulbs. Okay? Why does it matter? I mean, if any light bulb lasts longer, isn't it better? Right? Why does the consistency matter? Okay? But the thing is, if you have, I mean, this Japanese light bulb spread is wider, which means if you look at the left side, goes like this, compared to the Korean light bulbs. Okay? And that means more Japanese light bulbs fail early in their life. Okay? So instead of talking about the same number, right? This is maybe 1850, or Japanese light maybe 1750. Right? The same number of light bulbs fail at 1750 hours versus 1850 hours. Okay? So, you know, that's important because that is what's called the J.D. Power Survey of Initial Quality. Have you ever heard of this thing, J.D. Power? J.D. Power is a company that evaluates the quality of many things, not only the automobile, but many, even the insurance companies rated by J.D. Power. It's a rating company. Okay? So what they do is they survey the car owners. When you buy a car, a few months later you get a mail from J.D. Power. Okay? And they ask you to respond to some questions. How are you? How satisfied are you with this car? Was there any problem? And so on. Okay? So they do initial quality survey, which is typically 6 months to 1 year. Okay? And this is a very important marketing information, right? So if you are rated high by J.D. Power survey, you know, you use that for your marketing, you know, in the newspaper. We got this, typically it looks like this, right? Some trophy, okay? We were awarded by J.D. Power for the high quality car and so on, high quality of our car's new model, okay? So you don't want anything to fail early, especially early, right, within 1 year. Okay? So, you know, the Korean light bulb may fail slightly faster, maybe 100 hours earlier on average, okay, compared to Japanese light bulb. Okay? So I guess in this case, they decided to go with the Korean light bulb, okay, if that's the truth. Okay? So that's the idea. So mean is important, or central location is important, but the spread also matters, because spread shows the consistency of the numbers. All right? All right, so among the measure of variation or spread, we can talk about a few different things. The easiest one, the most primitive one, is range, and we already talked about it. What is range? Range is, largest number minus smallest number, okay? I think I added this. You don't have this in your note, okay, but I added this just for presentation purpose, okay? Because, you keep seeing these graphs, okay? As I said, this is a typical normal distribution, okay? And we have two different normal distribution, okay? Or, well, not really normal distribution, but you can say this symmetric continuous distribution, okay? Apparently two distributions share the same center, but we have different spread, okay? So this, I brought this graph from chapter 6, and you're going to see that again in chapter 6. How do we come up with this curve? Okay? Or what does that mean? Okay? Well, we talked about histogram, and we talked about polygon, frequency polygon, or relative frequency polygon. Okay? So you can consider any histogram and frequency polygon here, and here you can consider this as relative frequency. Okay? So 5%, 10%, 15%. Okay? So when you think about the frequency polygon that connects the top of the histogram, okay, just imagine these bars are many. So instead of here in one bar is from 1.055 to 1.05, so the width is about 0.005, right? 0.005. But you can make it even narrower, 0.001 or 0.00001, and so on. Okay? So you can imagine the histogram with the very narrow bars or many bars, okay? Then the curve or polygon can become very smooth, okay? So right now, that's all you need to understand, okay? So when you keep seeing these graphs, don't worry about it. We'll talk about the continuous distribution and normal distribution in the later chapters. Okay? All right, so range is simply largest minus smallest. Okay, so here, again, a couple of examples. If you have 5, 6 numbers from 7 through 12, okay, the range is 5. Okay? Well, in this case, we have 7, 10, 11, 12, 12, 12. 3 numbers, 3 12s. Okay? In that case, range is also 5, right? So it doesn't the actual distribution cannot be represented by range. Okay? Range simply represents the distance between the largest number and the smallest number. Okay? That's why it is a very primitive measure of the spread. Okay? But it is very sensitive to outliers, again, because we have, say, 2 different cases. They are identical distribution except for one number. Okay? So here, I don't know how many numbers here we have, maybe 20 numbers. Right? And the largest number is 5, smallest number is 1, so range is only 4. Okay? Here exactly the same numbers, but the last number is 120, extreme outlier, right? Then the range becomes so big, right? So it could be very misleading, right? Right? Because all other numbers are distributed between 1 and 4, but there's just one number, extreme outlier, that changes the range significantly. Okay? All right, now we're getting into real stuff. Okay? Variation or the variance. Variance is the most typical measure of variation. Okay? And here specifically we're talking about sample variation. There is sample variation and there is population variance. I'm sorry, sample variance and population variance. Okay? And well, what's the difference? Okay? First of all, this is the formula for sample variance. Okay? So in order to calculate variance, we typically use S squared to denote the sample variance. Okay? You first have to calculate the mean, sample mean, x bar. Okay? And then from each observation, you subtract the sample mean. So what's inside the parenthesis? Okay? It's called the deviation. In other words, many times we just call it deviation. Okay? So deviation of each number from the mean. So how far each number is from the central location. That's what this measures. Okay? And then we square each deviation and then add them up. Add up all those differences. Okay? And then divide it by n minus 1. Okay? So what's the concept of this? Why do we do this? Let me try to give you very, intuitive understanding of the concept of variance. Let's say we have 4 numbers, minus 2, minus 1, 1, 2. Okay? In one case. In the second case, we have also 4 numbers, but here we have minus 4, 2, 4. Okay? And which one should have larger variance? Between A or B? B. Why? Because the variance is the measure of, what is it? Spread. Okay? And obviously, these 4 numbers are distributed within narrower range. Okay? And these 4 numbers are spread or scattered within wider range. Okay? So this should come up, if you are going to use variance to represent the degree of spread, of course we should come up with a larger variance for this case, right? But if you do not square, suppose you just noted the difference between each number and the center. Of course, center is 0 in both cases, right? So I just did it to make the calculation simple, right? So if you just add it up without squaring, right, then it's going to be something like minus 2 minus 0 plus minus 1 minus 0 plus 1 minus 0 plus 2 minus 0. Okay? What does it have? What happens here? Minus 2 minus 1, 1, 2. And the summation will be 0. How about here? In the second case. Minus 4 minus 0 plus minus 2 minus 0 plus 2 minus 0 plus 4 minus 0. The total will be also 0. Right? So the negative, if you don't square and just add up the difference between all the numbers and the center, just to make notes of how far each number is from the center, then we got a problem. Because the negative deviation, all the numbers to the left of the center will cancel out the deviations of the numbers to the right. Okay? So we will end up saying, well, the variance of this data is equal to variance of this data. Okay? Doesn't make any sense, does it? Right? So in order to avoid this canceling problem of these different observations, we square. Because when you take a square, all the numbers become positive. Okay? So it'll be 2 square, 1, 1, 2 square. If you add them up, what? That's 10, right? Okay? And here we have 4 square, 2 square, 2 square, 4 square. Much larger, right? 32, what, 40? Okay, if you square. Okay? So that's the idea. So without the square term, you can say, okay, we are adding up all the differences or deviations and divided by pretty much the number of observations, right? So you can say the concept is average deviation if we hadn't squared, right? So that makes sense. I mean, what we're trying to find out is how far each observation from the center. Okay, so by noting the deviation or distance between each number and the center, if you add them up and divide by n, you can say this is average distance or average deviation, right? Which is a measure of variation or spread. Okay, but because if you just do that, all the right side or the positive deviation will cancel out the negative deviation, right? We square each deviation, right? So you can say, well, variance is, in concept, variance is average squared deviation, right? Does it make sense? We try to give you some intuitive understanding of the concept of variance. What is a variance? Variance is just simply average squared deviation. Okay? Well, here's one problem. Now, normally, if you calculate average, you add them up and divide by n, right? But why do we use n minus 1 here? It's strange. Okay? Well, we do that only when we are dealing with a sample. Instead of sample variance, we can talk about population variance. We use sigma square. Okay? Formula for sigma square is summation of xi minus mu. This comes in a little bit later, a few pages later, okay? But I think I should talk about it now, right? So when you calculate population variance, we subtract population mean from each observation, square, add them up, and divide by population size, the total number of observation. So that's exactly the concept of average. Okay? You add them up, average squared deviation. Okay? But when we are dealing with sample, we use n minus 1. Okay? Why do we do that? That's beyond the scope of this course. Okay? If you are really interested in finding out, you can look for Bessel's correction. If you are really interested in statistics, okay, you can do the search on the web for Bessel's correction, okay, and you can read about it. Okay. But it's a quite serious statistical theory. Okay. And basically the idea is when you're dealing with the sample, this one works better. It provides better result or more accurate result than using n. Okay? I guess I can spend a couple minutes. Yes?
Do you mind just explaining it
about the Bessel's correction? I do mind. Because I'm not a statistician. Okay? And as I said, that's way beyond the scope of this course. Okay? And again, you can easily read about this in the internet, right? But again, that's a very serious statistical theory. Right? It requires a lot more understanding than you have now. You have to understand the concept of distribution. Okay? Better than that, I'm trying to give you some more useful understanding. It's called, from now on, throughout this course and maybe next course, you'll keep hearing something like degrees of freedom. Typically, we just write DF, degrees of freedom. Sometimes degrees of freedom is n, sometimes degrees of freedom is n minus 1, n minus 2, or n minus k minus 1, something like that. So let me try to give you what those degrees of freedom mean, okay? Suppose you have a data set, okay? And let's say someone told you that we have 5 numbers in this data set, okay? And you are free to choose any number. So if I just tell you, okay, we have a data set, n is 5, okay? Then you are free to choose any 5 numbers, right? You can start with negative 2.6 zillion, okay? The next number could be negative 2.5, and 2.5, 250, 250 billion, right? You can choose any 5 numbers, right? So you are free. In other words, degrees of freedom is 5 in that case, okay? But if I say, okay, we have 5 numbers, okay, then I have x bar of 2.5. I give you one more information here, besides the sample size, okay? Then what happens is you can choose any 4 numbers, okay? Whatever, 3.6, negative 3.6 billion, okay? 1.7 trillion, whatever, right? You can choose any 4 numbers, let's say 250 billion or 3.7 whatever trillion, okay? Then the last number is already fixed because it has to satisfy this condition, right? Does it make sense? Does it? You get the feeling, right? You have 5 numbers. You can choose any 5 numbers, but you have to satisfy one condition. That is, the sample mean has to be 2.5, right? Then you can choose any 4 numbers, but once you did that, the last number is fixed, right? In order to satisfy this, right? So that means you lost 1 degree of freedom. Degrees of freedom becomes n minus 1 or 4. You can choose 4 numbers. Okay? So in statistics, that's an interesting phenomenon. Okay? Whenever you use the data to estimate one parameter, it could be mean, it could be standard deviation, right? You lose a degree of freedom. If you estimate 2 parameters, mean and standard deviation, right, you lose 2 degrees of freedom. Okay? So if I say, all right, we have 5 numbers, mean is 2.5, and the standard deviation is 1.1. Then you can choose any 3 numbers, but then 2 numbers are already set because it has to satisfy these 2 conditions. Okay? That's the idea of degrees of freedom, and we'll talk about degrees of freedom as we go on. Okay? But again, here you need to understand the intuitive concept of variance. Okay? It's average square deviation, okay? But the only thing is when you're dealing with sample, you use n minus 1 instead of n, okay? Since we talk about variance, we can easily talk about standard deviation. Yeah? Standard deviation is simply square root of the variance. Okay? So in order to calculate the standard deviation, you have to calculate variance first. It's simply the square root of variance. Okay? So here's a question you should ask. Why do we bother with both? I mean, since standard deviation is the square root of variance, right? If you have large variance, obviously you will have larger S, right? So in any, the whole idea is to measure the spread, how widely the data points are scattered, okay? And now we talked about the variance already, okay? But why do we go ahead and take a square root and calculate standard deviation? Okay? The idea is standard deviation has the same units as the original data. Yeah? So let's say we're trying to find out the variability of income. Okay? Suppose you have large data, and you want to find out how widely the data points or income values are spread. Okay? And you use the formula to calculate this variance. Okay? It comes out to be 1,050. Unfortunately, there is no meaning, practical meaning of this number, other than the size of the width. Okay? This is not measured in dollars, because actual incomes are measured in dollars, or won, maybe, Korean won, okay? But remember, while you calculate the variance, you squared the differences, okay? So the unit of variance is not the original unit, okay? But when you take a square root and convert them into standard deviation, so, okay, let's say it was 10,000, right? And when you take a square root, standard deviation comes out to be 100. This is in original unit, $100. Okay? So you can say the standard deviation of the data is $100. Okay? So for that purpose, we also calculate the standard deviation, right, in order to convert it or measure the difference in original unit. Right? Could be centimeters or kilograms or minutes or whatever the units of the data may be. Okay? Just one more slide here. Still have 5 minutes. Let's see. All right, so this is how you calculate it actually. Okay, so we have 8 numbers, right? And you can easily calculate, again, first you have to calculate the sample mean, right? So subtract the sample mean, which is 16 from each number, square, and then add them up, divide by n minus 1, right? So what's inside the square root here? That's, what is it? What's inside the square root is? Deviation is inside the parentheses, right? And you squared all the deviations, add them up, divide by n minus 1, what is it? Sorry, I'm asking very obvious question, right? It's variance, isn't it? Okay? So what's inside the square root is variance. If you take a square root, that becomes standard deviation, okay? So standard deviation is 4.3095, okay? You should be able to do that by hand for the case when you take an exam, okay? But in most cases, for practical cases, you should use Excel. Let me just show you. Just give me 1 minute here. Open up, come on. All right, so we have, give me the numbers. 10, 12, 14, 15, 17, 18, 24. Okay. So when you have these numbers, all you need to do is just, you choose any cell and type equal STDV. Okay? STDV. You see STDV here and STDV point P, right? They're slightly different. If you just say STDV, that's a sample standard deviation, so it will be divided by n-1. Okay? This is the population standard deviation, right? So it's going to divide by n, right? So that's going to be slightly less, smaller than sample standard deviation. So let me show you. Just say, there we go. 4.3094, that's exactly what we have in the slide, right? 4.3095, okay? I just round it, okay? All right, if you do STDV, you have to type equal first. Point P, and the range, right? Yeah, you got 4.03, right? Because this is divided by 8 instead of 7, right? So this is divided by 7, this is divided by 8, so slightly smaller, okay? Of course, you can calculate variance if you like. It's even easier. It's VAR. Yeah, again, we have VAR and VAR.P, depending on sample or population, right? So you can just use VAR and just highlight. Yeah. And of course, 18.57 should be square of 4.3095, okay? So for most practical purposes, when you're doing your homework, you can use Excel. But for the case you take an exam, you should be able to calculate it by hand. Okay? Any question today? All right, thank you. I'll see you next class.